Okay, picking up where we left off, we're now going to talk about partial molar Gibbs free energy changes in simple mixtures. And this will be very similar to what we talked about with partial molar volume changes in chemical mixtures. So we've introduced this concept of chemical potential. Okay, and I noted that is related to the Gibbs free energy. So for example, if we look at the Gibbs free energy at constant pressure and temperature and constant number of moles, we can replace that whole derivative with mu, chemical potential. Well, we could also do the same thing for our other thermodynamic potentials as long as we're holding their respective natural variables constant, right? So for example, Helmholtz has constant temperature and constant volume. And if we make that condition with holding all the other species constant, then we can also note that is chemical potential. And just like we saw in volume changes, if we look at Gibbs free energy changes, the slope of this line is going to give us that partial molar quantity. And of course, we could also have negative slopes as well. I know this figure didn't indicate that, right? But we could have a negative slope, which would indicate that the addition of some species lowers its chemical potential. And of course, a positive slope means the addition of that chemical species raises its chemical potential. So of course, writing out our full differential expression like we've done for a mixture of, let's say, A and B, we could write that as now the following. Okay, so, oops, that was a weird little spiky thing. Okay, so now that's constant pressure, constant temperature, and now number of moles of B is held constant for the changes in the number of moles of A. And then we'll do the opposite, where now pressure and temperature, and this time number of moles of A is held constant for changing number of moles of B. Okay. So if now we think about doing this at just constant temperature and constant pressure, dg, then let's see here, then we will have mu A and dNA plus mu B and dNB. Or if we want to now look at our total expression for dg, we know we're going to have the fundamental equation, v dp minus s dt. But now, if we allow for there to be a change in number of moles, we can also add this extra term. So, and that sum is to indicate if we had a number of species like A, B, or even C, D, etc. So now we have modified our fundamental equation of thermodynamics, and this is what we refer to as the fundamental equation of chemical thermodynamics. Of chemical thermodynamics, okay? All just from that change in number of moles, right? So let's see, if we keep moving on here, we'll introduce this new equation, the Gibbs-Duhem equation. So now working back to this, I'm going to rewrite that expression that I just wrote, noting that if we're talking about constant temperature and constant pressure, that's going to be, right, mu A dNA plus mu B dNB. Well, if we want to think about the total change in this thing, okay, we also have to consider the following, right? So we could consider that expression that I just wrote, mu A dNA plus mu B dNB, but we also must consider what happens if I hold the number of moles constant in A and now allow the chemical potential to change, d mu A, or NB plus d mu B, okay, d mu B. Well, we have this expression right here for constant temperature and constant pressure. And so given that both of these state that this is dG at constant temperature and constant pressure, we can set them equal to each other. And in doing so, we would arrive at the following conclusion. We would see that Na times d mu A plus Nb times d mu B must equal 0. All right, that's the only way to make these two things work, which is now where we arrive at the famous Gibbs-Duhem equation, which says something like this. The sum of our, let's write a better sum sign here. So summation sign, where I could be any species, Ni times d mu I must be equal to 0. So this is our Gibbs-Duhem equation right here. And upon doing some algebraic rearrangement for this simple mixture, for example, we could say changes, I don't know why it does that weird thing. Changes in the chemical potential of B must equal negative Na over Nb times d mu A, right? Just from arranging that algebraic expression. And so there's an important point that comes from this, and that is we can't change the chemical potential of one of these things without changing the chemical potential of the other. So in effect, that's just like those graphs that we were showing before. And of course, we could say the same thing about molar volume, right? Where instead of writing this as chemical potential of, sorry, I'm losing track here. Yes, so instead of writing this with just respect to chemical potential, we could also just go back and rewrite this as our partial molar volume, right? dVB, for example, equals negative Na over Nb of dVA. So these expressions imply the same thing. We can't change a partial molar quantity without affecting the partial molar quantity of the other species, right? And so that's exactly like the graph that was shown with volume versus mole fraction, where when one kind of dips down like this, the other has to kind of dip up in the opposite way, right? So where one has a positive slope, the other has to have a negative slope, and vice versa. So that's the important thing to note about the Gibbs-Duhem equation is we just can't, like, when we have a mixture, changing the amounts in the mixture changes the thermodynamics of the whole system. Okay. All right. I'll see you in the next video.